Hello, YouTubers. Dave Soriano. I'm a chemistry professor in the University of Pittsburgh system. I'm at the Bradford campus in Western Pennsylvania, USA. And one of my areas of research is the chemistry of art, with focus on new paint formulations for use as so-called oil pastels, oil sticks, and cold wax formulations. Now, the use of cold wax goes way back with the masters. Remington, for example, spent an awful lot of time with impasto variations of wax formulations. I work with paraffin wax, vegetable wax, jojoba oil, and in one approach, I simply melt down. I buy large 5 or 10 pounds at a time of broken crayons, Crayola, Rose Art, Crazy Art, other manufacturers. I melt them all down on a heat tray. Remove the, I used to put them into warm water to remove the wrappers, the paper. Then I use an X-Acto knife to cut it off. And then I found the easiest thing is throw them in big vegetable cans that have been used and melt them down with forceps. I just simply remove the paper and then pour the molten pigmented wax into silicone molds that I get at a local thrift shop. They work great. The purpose of this video is to let viewers know that I'm working in this area, and I don't mind sharing some of my results with the YouTube audience. Some of this will be of much greater interest to chemistry professors, particularly those working in contact with undergrads. There is and always has been an interest in the connection between chemistry and art, going back to the early cave art and rock art. And almost every museum would have, art museum would have forensic chemists that are involved in detecting forgeries, or with the ardent task of touching up master work. I was just looking at Van Gogh's Sunflowers, and they have to do touch-up work on the use of his chromium yellow. It's fading. The purpose of this is just to bring attention to the fact that Azo dyes are a significant part. Dyes and pigments are a significant part of the paint industry, with many applications. And for those new to this type of work, a pigment is essentially non-soluble in a solvent, particularly water or alcohol. You can have earth pigments such as the ochres, yellow, red, brown, and you can have basically pigments that are synthetic but not water soluble. I work with production of both Azo dyes, the water soluble forms, and the pigment forms that are not. And you can get some beautiful yellows, reds, oranges, browns. And this video will focus on two novel methods of making Azos. And as I said, there are chemistry professors throughout the world that may be interested in one of these techniques for carrying out Azo production, which typically is carried out with harsh acid and precedes the production of azos through the diazoniums, many of which are unstable and have been known to explode. And I have a couple of good methods that I just came across in the literature that I want to share with you. And then I'll show you a sneak preview of some of the work I'm doing. And any artists, I'm an amateur artist myself, but I'm trained as an organic chemist, and I'd be glad to interact with any viewers in case you want to try some of my materials out. Many of the materials I'm producing right now, as I said, are cold waxes formulated with pigment, and I send them on to the Boston Museum of Art, which has the second largest pigment and paint collection in the United States, right after Harvard's, and that's used by forensic scientists investigating crimes, as well as forensic chemists that want to see if they can match up or try to match up a pigment or dye that was used by an artist, even going back centuries. So let me bring up some slides here, and it'll be a brief, just a brief presentation. Bear with me, please. And I guess we'll start right here, huh? Azo Pigments, dyes, novel entries, art applications. These are pretty interesting methods, and I've gone through both of them and reproduced them. The first one I want to show you, this was published in the Journal of the Chinese Chemical Society, volume 56, number 5, 2009, and you can find the paper starting on page 1018. And the authors are Pesyan, Pesyan, Khalafi, and Malikpour in Iran, Urmia University in Urmia, Iran. This is a very interesting paper because the authors were able to show that they could produce a nice selection of venerable azo pigments or dyes using a grind method. 5 degrees Celsius, 5 minutes, mortar and pestle. I generally place the mortar and pestle in the freezer, in a lab refrigerator, cool it down, and then conventional stoichiometry. Here I'm showing beta-naphthol, 2-naphthol as a donor, and that would be subjected, if you want to make a dye, to an isomeric sulfonilic acid. Here it's obviously, it can be ortho, meta, or para. I use all of them. And you put that equal molar amounts in a mortar and pestle and grind for 5 minutes, and you will see a color development rapidly. It's a marvelous process and a wonderful experiment in beginning organic for students. And it can be scaled up. I've made as much as 2 grams at a time, maybe 3 grams at a time without incident, because these diazoniums that I'm producing are relatively stable. But you want to read the paper very carefully, of course. And then what you get is the Azo dye because of the catalysis, self-catalysis of the sulfonilic acid. You go through the diazonium intermediate, which I did not show, and you get the Azo dyes. I'm showing one isomer, and I'm showing the Z isomer, but with visible light, you can also isomerize it to the cisoid form. So here we have the Z form I'm showing you, which is the less stable isomeric form. And I'm showing just one isomer. I'm showing attack at the 1 position of naphthol. But you get beautiful, beautiful colors. It's reproducible. And in the next slide, we're finding that you can make pigments this way. And in this case, once again, I'm showing beta-naphthol. You need an acid catalyst, para-toluene sulfonic acid, and react that with an aniline of choice. And of course, I left out the amino group in the para position, but it's para-nitroaniline. Forgive me for that. Azo coupling occurs. In this case, you get a pigment because you don't have sodium sulfonate, water-soluble form. I use both the dyes and the pigments because in my work, I will then mull them with linseed oil and then blend with wax. But this is a very, very good. There's the reference for the paper. I think it's really an excellent, excellent process. Can it be scaled up to large scale for manufacture? It would be very attractive because you don't generate a lot of acid waste. You don't generate any acidic waste. And you're doing this in the solid phase. A little bit of water will form, and sometimes I'll add a drop or two of water. But whether it can be scaled up or not, we'll have to leave that to the chemical engineers, but it offers great potential. Now, another method I want to show you is a recent paper by Takeda et al. in Synthesis, the German journal Synthesis, known to organic chemists. This is Takeda, Okamura, and Minakata, and they are at Osaka University in Japan. This is a very, very interesting paper. You can do this one of two ways: self-coupling of an aniline in the presence of T-butyl hypochlorite. Organic synthesis, there's a procedure, very easily prepared. I buy the commercial T-butyl hypochlorite, and then it's converted to the hypoiodate with sodium iodide. You can do the reactions depending on the actual compounds you're choosing as reactants, -20 to room temperature, and you can get yields of 44 to 97%. And this is a very interesting entry into Azo. Push-pull in particular. If you were to use a para-substituted aniline, then organic chemists would realize you would get a push-pull Azo dye. And you can also combine, mix and match, but we'd like to note the authors have found that if you use a combination of electron-rich anilines, you will only get homodimers. You will get self-coupling. Excuse me. They're still exploring the rationale why that is, but if you take one that's electron-rich and react it with one that's electron-poor under the same conditions, they showed 15 examples, you get a 47 to 72% yield, and I'm able to take these pigments, some of which really have not even been prepared. It's not known how to do this, and then I'm blending it up as a pigment coloring agent in my paint formulations. And this is not really a suitable reaction, I would imagine, for undergrads, but research chemists and those working in the chemistry of art. And of course, I may add that chemistry, the early industry goes back to Perkins' synthetic dyes production in the beginning of the chemical industry, production of paints and pigments. Very, very interesting paper, and it came out in 2003. And what we have here are just some wax, cold wax formulations. But first, there's one of the Azos, a beautiful, beautiful brownish earth color. And when I do my painting, it's spectacular. These Azos. Are they fugitive? Yes, but I can't resist using some of these Azos. Here I reacted Vanillin. I pronounce it Vanillin. Some people call it vanilla, vanillin. Vanillin, one of the characteristic odors of vanilla from the vanilla bean, and carried out a reaction with the parasulfonilic acid, and produced the corresponding dye, and then blended it with kaolin. That's another story, but I look and work with kaolin dyes, the pozzolanas, such as what was found in the soil around Mount Vesuvius in Italy, Campana, outside Naples. The Romans used that to make concrete, and I work with a couple of mining companies in the western United States, so I'm also working with the kaolin families and blending the kaolin clays with these dyes, and I'll be formulating them, as I said, particularly in cold wax preparations. Here are some cold waxes I've prepared, some with color, some without. Melted crayons. We're giving you the cold waxes that were prepared. Many of these waxes, almost every one of them is different. Some are pasty, some are solid. Then you would take the latter, break it up, mix it with an oil-based linseed paint to make your cold wax for application with bristle brush, and use gesso on Bristol paper so the oil doesn't seep through. And I'm also, there's another story, but I'm making chemical hybridizations of waxes and oils by transesterification. But The Azos are not shown here, but very shortly I'll be using Azo Pigments and dyes in the cold wax formulations. And this is a close-up of one. And this was brown crayon mixed with oil-based burnt sienna commercial paint. And the cold waxes are given ratios of wax along with mineral oil. And if you want a drying formulation, you would use linseed or walnut oils. And I blend that together, the wax, if crayon, with the oil, the drying oil, or blend with pigment, mold with drying oil. And there you can see the swatches on the right, and that one shows the tannish color. So this is just to give you an idea of the research I'm doing, some for artists, some for undergrads. And if you want to contact me, Dave Soriano, University of Pittsburgh, Bradford in Pennsylvania, USA, Department of Chemistry. There's my email address. And thank you very much for watching the video. Bye for now.